All right, everybody. Since I am not there in person right now, and we've only got a few lessons to go before we're done with material and ready to start practicing for the AP test, I want to go ahead and make some videos for these last few lessons just to get you started and get you going. There are just a couple left. We're really almost there. We're at the finish line. So we're going to start with one today, and then possibly two more, and then you're going to be done, and it's all going to be AP practice from here on out. So what we need to talk about today are something called Taylor polynomials. And what Taylor polynomials are, in essence, is a way to express a function um, as an infinite number of terms. So in essence, sometimes these are called Taylor series because it's an infinite number of terms where if you add them all up, they would be exactly equal to whatever function it is you are working with. Now, we often use them, we don't not as an infinite number of terms, but just as a few terms. And what they allow us to do in that context is by using a Taylor polynomial, we can plug x values into our Taylor polynomial instead of into our original function. And it gives us a really good approximation of what the original function is. So that should remind you of tangent lines. In the past, let's say we had a function that looked like this and we drew a tangent line. Well, you can plug an x value into this tangent line instead of plugging it into the Taylor polynomial, or excuse me, instead of plugging it into the original function. And as you notice, as long as you stay close to that point of tangency, then our tangent line approximates the function pretty well. And a Taylor polynomial does the same thing, it just is more powerful. It approximates it more closely, and you can get further away from that point of tangency and still get good approximations. So we're going to talk about that here in a second. Now, one bit of terminology I want to get out the way is this place here where your line touches the function. In this lesson, we're going to be calling that the center. So when I say the Taylor polynomial is centered at x equals 0 or x equals 1 or x equals 2, that just means that that's where the polynomial is going to touch the function originally. We're going to base the whole Taylor polynomial about the function's meeting right there at that x value. Whatever the center is, that's where it meets. Or in the context of tangent lines, it's the place where the tangent line touches the function. So we're going to call that the center of these Taylor polynomials. All right, so here's essentially what you need. And when I first start writing this out, this is going to look like a lot, but I promise that after you do this a few times, it actually becomes not so bad. So the first term of a Taylor polynomial is just going to be plugging in your center, which is what c is, into your function and getting some value. Then you're going to add, and you're going to take the first derivative of the function and plug in the center. And then you're going to have x minus c. Then you're going to have the second derivative, where you plug in the center. Now we have x minus c squared, and it's all going to be over 2 factorial. And then the pattern just continues. So if I take the third derivative, we're always going to plug in c. Now we're going to have x minus c to the third, and that's going to be over 3 factorial. So if you notice the pattern, whatever you're plugging in, whether you're taking the first derivative, second derivative, third derivative, etc., let's just call that the nth derivative, whatever that is. You'll plug in c. Then you'll have x minus c raised to the n. And then all of that is going to be over n factorial. And you can just keep following this pattern for as long as you want to. And the longer you go, the better this polynomial is going to be at approximating the original function. Now, one thing I'll point out in a second, and we'll do this, if you actually stop right here, what you'll see in a second is that that is the tangent line. So if you only take a Taylor polynomial out to the first degree, where x minus c is raised to the first power, then you're going to have a tangent line every single time. It's identical to the tangent line that you've been doing all year. The Taylor polynomial is just different in that it keeps going, and the further you go, the more powerful and more accurately it will approximate the function. Okay, so let's start with a really basic example. Let's say we've got the function f of x equals e to the x, and we're going to center this, let's say at x equals 1. So what that means is everywhere you see a c in this formula, you're just going to plug in a 1. So if we do that, then what we have here is e to the x is going to be equal to f of c, which now is f of 1, And so f of 1, of course, is just e to the first, which is e, so that's your first term, plus, and the reason I said this is easy is because, of course, the derivative of e to the x is e to the x, and all we're doing is plugging in 1. So you're going to get e to the first for your first derivative term right here. And then it's going to be x minus 1 because we are centered at 1. So again, right there, we'll do this in a second. I'll show you on a graph. That's actually the tangent line. So we'll take a look at that in a minute. Now the second derivative is not going to be any different because the derivative of e to the x is e to the x. So the second derivative is e to the x. You plug in 1 and you get e to the first again. Now we have x minus 1 squared over 2 factorial. And you can just keep going for as long as you want. We're going to get e x minus 1 cubed over 3 factorial. And then on the AP test, a lot of times what they're going to want you to do is write something called the general term. And the general term essentially is a term with ends in it that allows you to summarize the pattern. What's happening? How could you generate the next term of the series? And so if you notice, every single term has an e in it. So we're going to start with e. And then it's going to be x minus 1 to the n over n factorial. And that is the general term that would allow you to generate any term you want of the Taylor polynomial. So if you wanted the term that was raised to the 8th power, just plug in 8 for n, and you've got it. All right, so there's a really simple Taylor polynomial. That one happens to be centered at 1, which makes it pretty nice. And of course, this one was great, again, because e to the x, every time you take the derivative of it, you just get the same thing over and over, which is why there's an e at the beginning of every single one of those terms. Now, let's take a look at the graph for a second and see what's happening here. So I've got e to the x graphed, and what I'm going to do is graph the Taylor polynomial on top of that. So if you just look at the first two terms, you would have e plus e times x minus 1. So let's graph that really fast. So that's e to the first plus, again, e to the first times x minus 1. And if I graph that, as I said earlier, all you've got is the tangent line that is tangent at the point x equals 1. And as like we've discussed all year, it's a decent estimate. As long as you stay fairly close to the point of tangency, you get a good estimate. But the further you get away from x equals 1, the worse the estimation becomes. So now to make it better, using our Taylor polynomial, we can just add in the next term. So we've got plus, let's do division here. On the top, every single time, you're going to have e to the first. This is going to be times, parentheses. Now in this case, it's going to be x minus 1 squared. And then on the bottom, you have 2 factorial, which in this case is just 2. And if you hit enter, notice that now it still touches at x equals 1. That's the center. But you can tell that it stays closer to the original function for longer. You can get further away from x equals 1, and the approximation is going to remain pretty accurate. And we'll test that in a second. If we want to go ahead and add one more to this, we're going to do plus, divide. As always, on the top, we're going to get e to the first. And we're going to say times, parentheses, x minus 1 to the third. And then on the bottom, you've got 3 factorial, which is just 3 times 2, which is 6. Hit enter. And as you see, it just gets better and better. So the more terms you add, the better your Taylor polynomial will approximate the original function. And of course, if you had an infinite number of terms, then it would be exactly equal to the original function. That would be called a Taylor series that we'll get into in more depth later. So there's the general idea. Now what we can do is test the approximation. So let's say, for instance, we just wanted to go out to the cube term and use that to approximate the original function. So f of 1 is my original function. Let's say I'm just going to plug in 1.5 and see what it gives me. So that's the exact value of the function at 1.5. Using our Taylor polynomial out to the third power or third degree, If I plug in 1.5 to that, you see that our estimation is really, really good. We're just off by less than 100th of a point there. And of course, if you were to add more terms, go to the 4th power, 5th power, 6th power, etc., then your approximations are just going to keep getting better. All right, so that's the basic idea of a Taylor polynomial. Let's do another one and try to get into a rhythm of doing these over and over again. So let's say in this case, we want to write a Taylor polynomial for f of x equals sine of x. And instead of centering at x equals 1 this time, let's center at x equals 0. So that is where we are going to center this Taylor polynomial. Now, when you center it at 0, it is sometimes called a Maclaurin. So if you see a Maclaurin series or a Maclaurin polynomial, it's exactly the same as a Taylor. It's no different. It's just a special case where your c is equal to 0. So just keep that in mind. It's a special term for that one instance of a Taylor polynomial. So that's what we have here. We have a Maclaurin series centered at x equals 0. So what do we need? Well, going back to the formula, I need f of 0, I need f prime of 0, f double prime of 0, and so on and so forth. And also notice, since c is 0, this is just going to be x, because x minus 0 is x. This is just going to be x squared. This is just going to be x cubed. That c term goes away, and it makes things really nice. So in this case, f of 0, of course, equals sine of 0, which is 0. Then I need f prime of x. Well, the first derivative of sine is cosine. And if I want f prime of 0, we have cosine of 0, which is 1. Now, the second derivative is going to be negative sine of x, but I plug in 0 to that, which gives me 0. My third derivative, I should be saying 0 here, sorry, is negative cosine of x, which is negative cosine of 0, which is negative 1. We can keep going. Our fourth derivative at 0 would be sine of 0, which of course is 0. And notice we have a pattern here. Our derivative is, well, our original function was 0, and then 1, 0, negative 1. If we went to a fifth derivative, we don't have to if they don't make us, but if we were to go to a fifth derivative at 0, it's going to be cosine of 0, which makes it 1. And so that's nice. Our derivatives are just going to alternate between 0, 1, negative 1, 0, 1. It makes this a really nice, simple series to create. All right, so sine of x then, if we are going to write this as a Taylor polynomial. It's going to start with f of 0, which is 0, plus our first derivative, which is 1. And then you have x minus 0, which is x to the first. So again, going back to this formula, our first derivative was 1, so it doesn't really show up there. And you just have x minus 0 to the first power, which is just x. So that's where that's coming from. Now, our second derivative is 0 again. So you're going to say plus 0 times x squared over 2 factorial. If we do our third derivative, we get negative 1, so that's going to be minus. You're going to have x cubed over 3 factorial. Your fourth derivative is 0, so you get 0 x to the fourth over 4 factorial. Our fifth derivative is 1, so you get plus 1 x to the fifth over 5 factorial. And we can keep going. Let's go back and simplify this. 0 is 0, so you have x. Now notice that your term with the second derivative here is 0, and that just makes the whole thing 0 and it goes away. So the next one is minus x cubed over 3 factorial. Your fourth degree term is 0, so that goes away. And so then you're going to get plus x to the fifth over 5 factorial. And hopefully you see a pattern now. You get to a point where you see what's happening. All of your powers are going to be odd, because anytime you have an even power, the derivative is 0, and those terms go away. So you have x to the first, x cubed, x to the fifth. Also, notice that all the even terms are gone. Of course, those are 0. You've got the factorials in the bottom that are the same. And notice that your signs are changing. That's what I was getting at, is that you've got positive, negative, positive, negative. So your next term is going to be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And you keep going. All right, so let's go back and take a look at an example AP question so you can get a feel for what this might look like on the AP test. All right, looking at 2016 here, we've got number 6. Give me 1 second here. All right, so looking at number 6, we have f is the Taylor series. The series just means the polynomial goes on for an infinite number of terms. It's about x equals 1, so that's where we're centered. So keep in mind that all of our c values then are going to equal 1 in our formula. It converges to f of x. That just means if you add up the infinite number of terms, it will be equal to f of x. Don't worry about the interval of convergence. That's coming in our next lesson. All right, they give us f of 1, which is great because that's the first term of our Taylor polynomial. They give us f prime of 1, which of course is going to be necessary to get our first derivative. And then they tell us the nth derivative is given by this formula here. And this is the formula we're going to use to get all of our derivatives past the first derivative, which they gave us. So for instance, to get my second derivative for the Taylor polynomial, that would be the second derivative at 1. That means all you got to do, if we're doing the second derivative, is plug in 2 for n. So we have negative 1 to the n, which is in our case negative 1 squared. Then on the top you have 2 minus 1, which is 1 factorial. And on the bottom you have 2 to the second, because again we're plugging in 2 for n. And if we simplify this, negative 1 squared is positive, 1 factorial is just 1, and on the denominator you have 2 squared. All right, third derivative at 1. Just plug in 3 for n. So I'm going to get negative 1 cubed. I'm going to get 3 minus 1, which is 2 factorial. On the denominator, I'm going to get 2 cubed. And we could just keep going. But I know in part A, they just want the first 4 terms. And so the 4th term is actually going to be the 3rd degree. So I'm going to stop right there. And let's go start filling this in. So in part A, let me erase this to give us a little more space. All right, f of x then is going to be equal to, our first term is f of 1, which they told me right here is positive 1. Okay. Then my first derivative is next, and that one's negative, so I'm going to subtract, and I get negative 1/2, which is my first derivative. And then in parentheses, x minus 1. Because again, remember in our Taylor polynomial, we've got the y value. You've got your first derivative times x minus c, and in this problem, c is 1. And so we just get x minus 1 to the first power. Then your second derivative is 1 over 2 squared. So I'm going to say 1 over 2 squared. You could write that as a 4, but I like to keep it as 2 squared to better help me see the pattern, to see what's going on each consecutive term. And then we're going to get x minus 1 to the second. And of course, we always divide by n factorial. So in this case, if it's squared, on the bottom we have 2 factorial. Our third derivative, we didn't simplify that, so let's go back for a second. Negative 1 cubed is going to be negative. On the top, 2 factorial is just 2. And on the bottom, you have 2 cubed. So there's our third derivative, minus 2 over 2 cubed. And then, as always, in every Taylor polynomial, we're going to get x minus 1 to the third over 3 factorial. And you can go for as long as you want. Now, they wanted the first 4 non-zero terms. We've done that. 1, 2, 3, 4. They also want the general term. So if I were to keep going, the question is, what is the pattern that is generating all these? Well, I already know the pattern and the formula for the derivative because they gave it to me. So for every derivative, you're going to do negative 1 to the n minus 1 factorial over 2 to the n. And then for every Taylor polynomial, you're going to multiply by x minus 1 to the n over n factorial. And that is the pattern we're following to get every single one of these terms. You could absolutely simplify that And if you look at the scoring guidelines for 2016, they will. You know, we talked the other day about how you can divide n minus 1 factorial and n factorial and simplify that. But you don't have to. You know, in free response, you can leave it just like this. That's a valid answer. That would get full credit. And so there you go. Now, we won't do this whole problem, but if you look down at part C, they say use the first three terms to approximate f of 1.2. And notice they call it an alternating series because it is. It's positive, negative, positive, negative. And that's really nice. We talked about alternating series and error, how the error of an alternating series is always the next term in the series. But in part C, they want you to use the first three terms to approximate f of 1.2. So you just say f of 1.2 equals 1 minus 1/2. 1.2 minus 1 is going to be 0.2, plus you would have 1/4. Again, 1.2 minus 1 is 0.2 squared. And all of that is over 2 factorial. And there you go. You could use that as your approximation of the original function, only using the first three terms. So whatever that equals, you don't have to simplify, of course, being free response, but that would be your approximation there in part C. All right, so again, the gist of this lesson, what's really important, what you really need from this, is you need to be very, very, very comfortable for using this formula. All right. To be able to generate a Taylor polynomial, or if they ask for a Maclaurin, remember that's when C is equal to 0, for any function. If they say, here's a function, write a 4th degree Taylor polynomial. That just means you need to follow this formula here out to the 4th power. And the more comfortable you can get with this formula, of course you need to have it memorized, the more comfortable you get with this, the more points you're going to get on the free response section of this test, and the easier it's going to be. Because again, getting comfortable with this pattern makes it pretty easy after you practice it enough. And they ask this quite a bit. I'm not going to say every year, but the majority of years you do have to generate a Taylor polynomial of some sort. And so knowing this pattern will make your life a whole bunch easier. All right, I'm going to give you some practice on this. And again, if after you do this a few times, it should get easier. Please reach out to me with any questions that you have. We've only got 1 or 2 more lessons to go before we get into full-on exam review, and so we'll get there soon enough. Thank you all, folks, and again, please reach out if you have questions, and hopefully I will see you all soon.